Sorry. In case you had anybody that was going to connect. Okay, I believe we're live on a different link now.
Can you send me the link when you get the chance?
Yeah, I'll just go ahead and. Sorry, this is getting. I'll just make an live now. Get shared the link. Let me see.
Also, can you allow me to share my screen?
Yeah. So let me know if that one shows up. Sorry about that. Sorry, I forgot how to make co-host. See if you can click share screen now. Does it allow you now?
Yeah.
Okay. And have you clicked the current link for the live stream?
Yeah, I saw my face on the live share. So
okay.
Let's see.
I guess we'll give it a few more minutes. People to come in. So then everybody should have the new link now on the CSIM. So I think most people would join the call directly. I guess we can give it a few more minutes in case people come trickling in. How are you doing today, Abe?
Pretty good. How are you?
Pretty good. You said your talk scheduled for about 35-ish minutes, so you have plenty of time for questions. So we can give it a few minutes for people to trickle in, I would assume.
Yeah, I don't know if you guys have done this over Zoom before, but I mean, previously when I went to these things, there was like a lot of like one-on-one Q&A afterwards. I don't know how that
Yeah. Yeah, we haven't done one on Zoom yet, so this will be our trial run, I guess. So are you at home today?
Yeah.
Yeah. So do you guys have, you said you guys are like 50-50 online in office type of thing.
Yeah, so we were almost all work from home until like basically like right before I started, and then we've been sort of slowly transitioning.
Nice. Yeah, that's good. So how many people are in work at Striveworks?
We're at about 30. So we also recently partnered with, we entered into a partnership with Deloitte. So they send us people
Oh, okay.
that we work with, but in Strive alone, it's like 30-ish.
Nice.
But we're definitely hiring. So if you guys are interested.
Awesome. So like, I guess how many of you guys are software engineers and how many are, I guess, HR/other logistics? Are you mostly?
So for ops people, there's 4 or 5. And then everyone else is on the technical side.
Awesome.
And even a lot of the ops people have, technical experience.
That's awesome. Cool. Okay, we'll go ahead and get started then. So I'm pleased to host Abe Frei-Pearson. So he obtained his PhD in mathematics from UT. How pretty recently, right?
In August.
Yeah. Okay. So very recently. And he worked on harmonic analysis and smooth interpolation problems. He's currently working at Striveworks, working on computer vision. And today he'll be talking about how he uses semi-supervised learning for tasks such as image classification, image segmentation, and object detection. Without further ado, I guess, Abe, you can start.
All right, thanks, Tyler. Yeah, so I'm Abe. I know some of you, and I'll get to meet the rest of you. So yeah, I've been working at Striveworks since September, and so today I wanted to talk about some things I've been working on, and sort of give a sort of broad overview of computer vision. So yeah, so the outline is I'm going to start by talking about who Striveworks is and what we do, and then I want to give an overview of computer vision. And then at the end, I want to talk about some of the things we've been working on related to semi-supervised learning and also active learning. So Striveworks is a data science and machine learning company. So we create both data science and machine learning tools, and we also provide services. So typically we'll have customers that have a huge amount of unstructured data. It's just hours and hours of video footage, and it's currently processed by multiple manual workflows or not processed at all, and they want to use this data to make decisions. So we need to design tools for them, and a lot of times this involves computer vision, but a lot of times you also have to use just more vanilla statistical techniques. And so we build products and provide services to help them analyze this data. Cool. So feel free, you guys, to interrupt whenever you feel like it. I know these things are usually much better when they're interactive. So do you guys have any questions about that? Okay, awesome. So I'll start by sort of giving a broad overview of computer vision. So what is computer vision? So this is how we use computation and statistics to extract knowledge from image data. So that's a pretty word salady definition. I think I got it from Wikipedia. So a typical computer vision task is, typical computer vision tasks are image classification, object detection, and image segmentation. So something is computer vision when you see it, right? You're using a statistical technique to draw an inference about an image. That's computer vision. So image classification is, this is sort of an example of an image classification task. So image classification is where you have a family of images and you want to assign them certain classes. So this thing I've gotten is from something called Fashion MNIST. So this is a data set of images where each image is a sort of low resolution image of an article of clothing. And so the task associated with this data set is to, to come up with a classifier that correctly classifies each image. So you want your classifier to output, given an input that is of a dress, you want it to say this is a dress. So that is one common type of computer vision task. So another is object detection. So object detection is a more involved task. So this is where you have some classes of objects and you want to, given an image, you want to draw bounding boxes around the objects that exist in your image. So for example, in this image, you've got a bunch of pars, and the output of the object detector is a bunch of bounding boxes, and oftentimes you also have class labels. So it'll say this is a red minivan or something, and it'll also give you the probability or a number which can be dangerously interpreted as a probability that the prediction is correct, or confidence score. So another task is image segmentation. So this is where you want to basically partition your image into components that are similar in some metric. So in this case, this image segmentation model, picks out different parts of the image that are similar to each other. You can think of this as like a pixel-wise classification task. Okay, do you guys have any questions about those things? Awesome. Okay, so how do we tackle computer vision tasks? So in the last 10 years, there's been a huge amount of development on these tasks using the technique of deep learning, which you've heard a lot about. Deep learning is using basically the technique of using artificial neural networks to do statistical inference. So I'll start by sort of giving an overview of what artificial neural networks are and then how they're used for computer vision tasks. So an artificial neural network, or a multi-layer perceptron, is a function from one Euclidean space to another Euclidean space, which consists of repeated compositions of affine functions and nonlinear functions called activation functions. So the affine functions we're going to call AI, and the activation functions we're going to call sigma. And here sigma is often the something called the rectified linear unit function, but it's just the positive part of each component. So you take, so the ReLU of a vector is you just take each component of the vector and you take its positive part. So the family of neural networks is a very broad class of functions, and in particular, it's you can check that neural network with a ReLU activation function is a piecewise linear function, and you can also get any piecewise linear function in this way. And so neural networks have very broad approximation power. So since you can get arbitrary piecewise linear functions, you can approximate any continuous function in a compact set, for example, using a neural network with a certain architecture. So the key task in computer vision often consists of finding the appropriate parameters of the affine functions AI, which are the weights and the biases. Okay, does that make sense? Do you guys have any questions about that? Okay. So convolutional neural networks are artificial neural networks where the affine functions are restricted to a particularly small class. So these are affine functions where the linear part is convolution with a particular convolution kernel. So you view your input I, if it's, for example, an n by n pixel grayscale image, the affine function aij is going to be convolution with a kernel k, which has support near 0. This is often useful for computer vision tasks. Well, for one thing, it's because, for one thing, these are much simpler. So a convolution kernel has a lot fewer parameters than an arbitrary affine map. And also it allows you to localize information and analyze these things in a homogeneous way. So in practice, when you have a computer vision model, you'll have a neural network architecture that includes some convolutional layers, some fully connected layers, as well as other components like max pooling layers and things like this. So yeah, those are CNNs, and they are what we use to do inference. Do you guys have any questions about that? Does the concept of a CNN make sense? Okay, awesome. So here I've taken this image to sort of give you an idea of what a CNN looks like. So you'll take an input image, and then you'll apply a convolution kernel so in this case, you apply a convolution kernel which produces a bunch of output channels. So you apply a different convolution kernel to get each channel, and then you do max pooling, and then you apply another convolution kernel to each channel to get a bunch more channels, and then eventually you do this a bunch of times, and then at the end to get the output of your network, basically you append a fully connected layer at the end, and that produces the output of your network.
Wait, sorry, I missed this then. What does this max pooling operation do?
So it's basically downsampling each channel. So it's not really important, but basically what it does is it takes every 4 pixels and just flattens them down to the maximum pixel intensity on each pool. So like, yeah, if you 2x2 max pooled just a 2x2 image, you would just get the single maximum element of that guy. Okay. So I talked about 2 things. One, I talked about computer vision, which is sort of these down-to-earth tasks like image classification and object detection. And then I started talking about these abstract functions between Euclidean spaces. So how do you actually use neural networks to perform computer vision tasks? So let's say we wanted to use all of this to help classify images into, say, C different classes. So we're going to pick an artificial neural network with a specific architecture. So by an architecture, I mean so like that diagram I showed you on the previous page. So you have to choose, what are the intermediate dimensions? Are the linear maps convolutional? Or are they max pooling, et cetera? So an artificial neural network. So we're going to do inference using an artificial neural network with a specific architecture. And so once we've fixed the architecture, a neural network is parameterized by finitely many real numbers, which we'll call WI. We're going to take our predictor to be G, which is the softmax of F, where the softmax is just this function I've written here. So it takes an arbitrary C-dimensional vector and returns a vector with positive entries that add up to 1. So this is a vector that lives in the probability simplex. So as I was saying earlier, there's some danger in actually interpreting this as a probability, but it's a probability vector. So the danger is that when you actually train this thing, so to skip ahead a little bit, when you train this thing to predict your image, to perform your image classification task, if you interpret this as a probability, it's not well calibrated. So it's typically overconfident. So it'll give you the right class, let's say 90% of the time. But if you interpret that softmax output, the softmax output might say like 0.999. It's very certain that it has the right thing. I guess that's getting ahead of myself a little bit. But so in any case, we're going to take our predictor to be this function G. Okay, how do we train this function, or how do we determine the weights such that this function performs our image classification task? So given n labeled training examples where Ci is the class of the ith example, we want to minimize the cross entropy loss across our training set. So this is this expression I've written on the bottom here. And so this is 1 over n sum of negative log g of xi sub ci, where ci is the is again the class labeled. So you can check that minimizing the cross entropy loss is equivalent to maximizing the likelihood. So if you do interpret this function g as a probability, this is basically equivalent to finding the weights such that the true labels would have the maximum probability of being predicted. Yeah. So do you guys have any questions about that? Okay, great. So this is called the training loss, and it's a differentiable function L of the weights W so I. So we seek to minimize this by using gradient descent and repeatedly replacing the vector W with W minus by basically a step in the opposite direction of its gradient. So we're trying to aim towards the minimum of this thing, and so we're stepping in the direction where it decreases the fastest. Except that second bullet point is totally a lie. So we're not really going to use gradient descent, or in practice, you're not going to use gradient descent on the entire training set to train this guy. You're going to use mini batch gradient descent. So you're going to take a random sample of the training set of size, which is much smaller than the training set, and you're going to update W by something proportional to the loss just on this sample. Yeah, so you just take the cross entropy loss that I gave earlier, but only on the sample S, and you update in the direction of its gradient. So this is stochastic gradient descent in the sense that the expectation over samples S is equal to the gradient of LS is equal to the gradient of L. So this is how we seek to minimize the training loss. Already there's sort of some mystery here because, okay, for an artificial neural network L, you can check that this function, or for an artificial neural network, you can check that this loss function is not a convex function of the parameters W. So why exactly does using gradient descent not get you stuck in some ridiculous local minimum? So there are a variety of explanations for this, but already it's sort of something that is just empirically this works. There are a lot of things in this field that just kind of empirically work. And this is maybe one of the simpler ones. Gradient descent just seems to work here. Okay. So that's well, before I go on. So that's sort of, I tried to walk you through the basic conceptual setup of how you train an image classifier. Do you guys have any questions about that?
If you don't mind.
Oh, good.
Yeah, isn't there another probability term in the entropy? Isn't it P log P?
Oh my God, yeah, you're,
Yeah.
well, so sorry. This should,
that's how I learned it, I don't know. Yeah.
This should be, there should be a sub CI. So the probability term is going to be 1 hot, right? Because you know what the label is. So one of the probabilities is just going to have 1 on a single entry. So I think it's correct here, where you have GXI sub CI. This is equivalent to multiplying this probability vector by, you 1 hot encode C, and so you multiply it by that, and you're just left with 1 component. And that should similarly be on this slide, but it's not because there's a typo.
Sweet, thanks.
Did you guys have any other questions?
Yeah, I was just curious regarding stochastic gradient descent, if there are other methods that I guess empirically work. I know I'm familiar with stochastic gradient descent as being like, this is one of the most commonly used because it works well empirically. So I was just wondering if you know of any other types that are also of interest.
So there's a lot of like stuff that is sort of builds on stochastic gradient descent. So there's, so for example, one thing that is used is momentum. And so this is where rather than, rather than taking a step in the gradient, at each point, and completely forgetting about the previous gradients. Instead, you take the gradient to be a weighted average of the current gradient plus the ones you previously computed. And this is called momentum. And there's a nice picture. It's useful if you have a situation where you're in like a valley where sort of you're here and your gradient keeps pointing you almost entirely in this direction, but really you want to be headed in this direction. So you can imagine like a mountain pass with a very steep slope that's headed downwards. Momentum can help you get down that slope a little bit faster. But sort of this is like an industry. So figuring out ways to minimize these functions, there's lots of them. I know, I mean, there's other methods for minimizing functions like simulated annealing is an example, but I'm not sure if that's used in deep learning anymore. So that's like where you, so if you have a function u that you want to minimize, you draw randomly from the distribution, which is proportional to like e to the negative alpha u. And then as you send alpha to infinity with high probability, that'll be at the minimum. Cool.
Can I add something?
Yeah, go ahead.
Yeah, I'm always under the impression that Atom is like a really popular optimizer. I use it by default on everything I do. I just don't really know much about it.
Yeah, Atom is another one. Let's see.
Ada Delta is another one.
Yeah, there's other ones like RMS prop. There's a lot of yeah, there are a lot of techniques. They're usually though they're all built on top of SGD, right? They're like SGD plus some other.
Yeah.
Okay. Cool. Yeah. Do you guys have any other questions? Awesome. Okay, so I want to briefly discuss a technique for object detection. So this slide is very terse. So I just want to sort of give you a very broad idea of how you might use a CNN to perform object detection. So I want to talk about a object detection method called CenterNet. So this is in a paper called Objects as Point, published by these guys, who I think some of them are actually in the UTCS department. So CenterNet consists of a CNN mapping an input image I to C+4 channels, which are downsampled by a factor K, where C is the number of object classes to be detected. And so the way you interpret this is the first C channels are like heat maps. And the values of these C channels can be interpreted, or I wouldn't say they can be interpreted, but maybe being very rough, let's say they're like the probability that there's the center of a bounding box lives at this point. And so to get bounding boxes out of this heat map, you pick some threshold and you say, okay, I'm going to take the centers of these heat output maps that have the highest values, and those are going to be the centers of my detection boxes. And then the last 4 channels give you the height and width of these of the bounding boxes, as well as an offset to undo your downsampling. The CNN is then trained on a made-to-order loss function that empirically works to basically to correctly detect objects in this output image. So in particular, the loss function on the heat map components is something called focal loss, which is it's like cross entropy loss, but where you're raising different the terms to certain powers. And then object detection is a pretty involved procedure. So you have to also say, okay, given a labeled image, which is just a thing that you've drawn a bunch of boxes on, how do you get this heat map from it? And their technique, I mean, it's basically to add a Gaussian term. So to add a Gaussian term to the heat map, where the parameters of the Gaussian are like proportional to the dimensions of the box. Okay, that is probably too terse to get a very thorough idea, but does that make at least a little bit of sense?
Yeah, I must have missed this as well. What is focal loss here?
Yeah, so focal loss. So when you so like I was just saying, when you have when you have a labeled image, you can you then use some procedure to get what you think its heat map output should be, and then you train your prediction on focal loss with that ground truth heat map, and the focal loss then is like the pixel-wise cross entropy, but where it's a modification of the cross entropy where the log term is like raised to a power. Yeah. Okay. Do you guys have other questions?
I was wondering, how is this like different or similar to some of the other object detection methods like YOLO and the rest? Are they?
So it's pretty different. So YOLO, a lot of these guys, a lot of object detection algorithms have like something called anchor boxes. So this is where like they basically specify in advance what the bounding boxes can be, and then they choose out of all the anchor boxes which are the ones that are best and what is their class. So in this one, it's sort of different in the sense that you actually learn just the center of the box and then what its dimensions are. Yeah. Does that?
Yeah. It was more of an open-ended question to like sort of see how this does versus others, or why we should choose this sort of a method. Why did you choose, for example, this sort of a method over others?
Yeah, I mean, so this is what we have implemented in our in our software. So the real answer actually is that YOLO has a very restrictive license.
Okay, interesting. I didn't know that. Okay.
But also I find this technique like very conceptual. I mean, it's involved, but actually I think it's like conceptually well motivated, I would say, to train a detector to learn all of these.
Okay, yeah, I guess you're not limited by the dimensions of the box, and you get to learn that because you only detect the center in this method, right? I guess.
There are other methods. There's something called CornerNet where you do something similar to this, but instead you learn what the corners of the boxes are. But I think this performs better than that.
Okay, thanks.
Okay, so in the last part, I want to talk a little bit about semi-supervised learning and active learning. So the things we've discussed so far have been supervised learning. So this is where you learn to perform a task given labeled data. So often labeled data is very scarce. So this lack of labeled data can be actually the bottleneck to good performance of your model. Semi-supervised learning refers to techniques that use unlabeled data to help train your model for your downstream supervised task. So the idea is you have a little bit of labeled data, a lot of unlabeled data. You want to leverage your unlabeled data to help you with your supervised task. As an instructive cartoon example, there's this thing. This is called the 2-moon data set. So let's imagine that your input data is this 2-moon data set, and that's all of your data. But you only have 2 labeled examples. You have this one example which is labeled white, and this other example which is labeled black. And you want to classify the rest of your images as white and black. Well, if you only look at your labeled data, you might be tempted to perform the classification which is done on the top image, which is where you just cut it in half. But once you look at your unlabeled data, you'll see that's like sort of unnatural, right? The clusters that your labeled data form are naturally these two half moons. And so maybe a more natural classification would be to call the lower half moon white and the upper half moon black. Yeah, so that's sort of the simplest example where semi-supervised learning can help. Does that make sense? Cool. So in the context of deep learning, often what happens is you want to learn a representation R, which I've called R for some reason, using unlabeled data, and then you want to train for your supervised task. Then you want to train a network on top of your representation. So one example that we've looked at is something called SimClear, which was a paper which was published earlier this year by these guys. I think they're at Google. So the idea is to train a representation R, which is a composition. So while you're training your representation, you treat it as a composition of three maps. So you have two neural networks, P and N, and then T is going to be like a random transformation of your image. So there's sort of some traditional ways to transform images. So for example, you can randomly crop them or flip them or apply Gaussian blurs or color jitters, do them or cut out parts of the image. So the idea is on a given batch, you apply this random transformation and then evaluate, you evaluate then your neural network on this thing. And so in a given batch, you have K different images, and for each image, you take two copies, and then you get two outputs for each pair of images, which you want to be similar. So in general, they're not going to be exactly the same because you're applying this random transformation to them at the beginning. But you want the outputs corresponding to the same ground truth image to be similar. On the other hand, you want the outputs corresponding to different ground truth images to be different. And so there's a made to order loss function corresponding to this thing. And if you train on this, you end up getting good representations that seem to work well. So there's some impressive results where, like on popular data sets, you can get close to state-of-the-art performance just with a tiny fraction of the usual labeled data set, just by training your classifier, for example, on top of the SimClear representation. So yeah, maybe I want to emphasize that, like I said, a lot of this is very empirical, and so there's a lot of tricky steps that I guess just need to be determined empirically. So for example, in SimClear, when you're training your representation, you'll see I've written it in sort of this strange way as P composed with N composed with T. So why did I do that? The reason is that when you're training, you train both P and N, but then when you're actually using it as a representation, you drop P. So, why do you do that? There's good arguments for why you ought to do that, but they're not that good, right? It just seems in practice to work. And sort of that's kind of the nature of this field. There are a lot of things that just seem to work, which makes it sort of interesting. So the last thing I want to talk about is active learning. So in active learning, you use a partially trained model together with knowledge about the distribution of data of unlabeled data to select new examples to be labeled. So the idea here is, if we go back to our 2 moons data set, let's say that you had an oracle and you could query the oracle to ask, what are the classes of another five of these dots? Well, if you were thinking hard, you really wouldn't pick the 5 dots that are closest to the guys you already have, right? You would want to choose other ones. And so active learning is sort of the study of how you do that. And so one technique we've tried is to train an ensemble of models and then to select the examples among the unlabeled data with the most model disagreement. And this does seem to give you slightly better training performance if you then train on these examples. Another thing that we've done is select examples where model outputs are not invariant under basic similarity transforms. So like when I talked about SimClear, we talked about using these data augmentations like cutout or random crops. Well, if doing random crops or color jitters results in your model not outputting the same classification, maybe that's a good indication that this is an image that you ought to train on. And so we found that at least in some cases this does result in less data hungry, a situation where our models are a little less data hungry. Okay. So some of the challenges we're working on is adapting these things to object detection and new contexts. And so because everything here is so empirical, it's often the case that when you want to apply these things in a slightly different setting, you have to make a lot of changes, or things don't work the same way that you might expect them to. So it sort of takes a fair amount of elbow grease to actually get these things to adapt to different different cases, and that's I guess part of what we do at Striveworks. Okay, so thanks so much for tuning in. Feel free to ask me any questions, and I put up my email if you want to email me other stuff. Yeah. Do you guys have any questions?
Yeah, I was a bit more curious about how this work. How do you use this work for different applications at Striveworks? More on the uh, application end of things. I feel like, is it just like client dependent, and they'll come to you with a problem and you try to find the best thing that works for them?
Yeah. So oftentimes our clients will have situations where they need these models built, and so most of my work has been on the back end so far. So I haven't. So at Striveworks, we do spend a lot of time working directly with the customer, but that's not something I've gotten to yet because I've only been here for 3 months. But my impression is that oftentimes you have situations where you need one of these models to be spun up in a very short amount of time, and really getting this label data, getting this data put together, and getting this model trained as quickly as possible is very time sensitive. And so what we're aiming for is to try and be able to spin up one of these models in under an hour or something, or under a day. So yeah, does that answer your question?
Yes, yeah, somewhat. Like for example, like do you know like how long your current project is? I'm just trying to see how different it is from like research, where you decide that you want to work on a problem for like a long period of time, and you learn so much and you try stuff in that field. But in your case, is it like, are the models generalizable, or were like other sort of problems that you will encounter from different clients, or is it like constantly changing and stuff?
So it's certainly, I would say it's not the same as my research career, where I sort of banged my head against the same problem for a few years, and eventually, you are able to make quite a bit of progress. But typically things move around a little bit faster, and you want to move forward, and there is maybe a greater variety of things that are asked. So yeah, in this talk I've mostly talked about like computer vision, but that's certainly not all that we do, and it's not even all deep learning. A lot of times these problems are best addressed just vanilla clustering methods that get the job done.
Right, yeah, that's cool, interesting stuff.
Could I ask a question?
Good.
Could you cover what metrics you're using? So for instance, for classification and stuff, just like the metrics part of what you do.
Do you mean like metric learning?
No, like mean squared errors. I don't know.
Oh, I see. Yeah. So for classification, I've usually used like cross entropy loss on the softmax outputs. So in principle, you can use mean squared error. For a while, we were trying to use mean squared error in, or at least I was trying to use mean squared error to use active learning. So there's some papers that suggested that you can select new examples to be labeled by choosing basically a subset of the unlabeled data that covers. So it covers the set in an L2 sense in the best way possible. I guess we didn't really find that to work all that well, but that's sort of off base from what you asked. So yeah, so for object detection, oftentimes you end up using focal loss, and then for for these representation learning tasks, often you have like a very made to order loss function.
Okay, so outside of like a deep learning approach, would you guys use just like a DB scan or something, or like a K-means or something?
Yeah, that's I think we use DB scan in some of our stuff. We use some other clustering algorithms like
DB scan is great.
There's one called Chinese whispers that we use. Yeah,
cool.
Just like a graph clustering method.
I had a question for you, Abe. Who did you work with at UT first? I was curious.
Oh, I worked with REA Israel. So I don't know if you know him, but you probably know his wife, Rachel. She does a lot of stuff with Odin.
Yeah.
Oh, cool. I was wondering what your transition was like from academia to industry. Is this something you always knew you wanted to do, or?
So this was something I decided on a couple of years ago that I thought, I don't know, I think the long time horizon of academia was not for me. And also sort of it does kind of restrict where you can go and you know, I don't know, you have to go chase a postdoc.
For sure.
But I would say, I mean, I definitely enjoyed getting, you know, they're sort of both, they're both great, right? So doing academic research is great. You can pursue something that you get really interested in for a long time. But I don't know, I found this transition also, it's a lot of fun, right? There's a lot of things to learn, and certainly on board. It's yeah. So as far as like, if I have any advice on the transition, I would say like, well, you guys are CSEM people. So maybe this advice is stuff you already know, but it's important to be, you know, a very competent programmer if you want to make this transition. That's how you spend most of your day.
Do you have to do a coding interview? Or,
yeah, we did. We do a coding.
Have you done any sort of internships beforehand in grad school?
No, man, I was all research.
Yeah, same here. Cool.
Can I ask if Striveworks is going to hire interns for the summer or something?
Oh, that is a good question that I should know the answer to. So we are not sure if we're hiring interns right now, but you should email me if you're curious.
Oh, yeah, thanks. Yeah, I'll shoot you a resume.
Yeah, I was just curious as to do you have any idea of how many people, like how many clients are managed by Striveworks as of right now? Like I know yesterday or Monday you mentioned to me that you guys have some contracts with Department of Defense, but I was wondering how many organizations, if you know.
I don't know if I can. Yeah, I don't know exactly what the answer to that question is. It's not like we have one contract, so we have a few contracts. Yeah.
How big is your team? Or do you know how many people are at Striveworks in general?
We're about 30, I think.
Okay.
So yeah. And team is like, if you mean who I work with directly, it's well, there's like people I work with more, but I guess the most directly there's like 5 people.
Is your day-to-day very collaborative in nature, or? I guess
yeah, it's pretty collaborative. I mean, it's not, you know, you're not sitting at the desk with somebody all day, but usually you end up, you know, checking ideas off of each other.
Yeah.
You know, pretty frequently.
No, that sounds nice.
Are people mostly like people just out of grad school, out of undergrad, or like super experienced in the field? How is like the composition?
So it is, let's see. It's not mostly people just out of undergrad. So we have, I don't know, we have a pretty high number of PhDs. So like, well, I guess some of the people there you probably know. So Eric Corman, well, maybe not, you guys are a little bit younger. So Eric Corman is the chief science officer, and he was a postdoc in the math department a few years ago. And George Torres currently works there, and he's a PhD student in math. And so then then I would say it's like maybe 50-50 between, you know, PhDs and people who don't have PhDs, but they're not, I would say there's only a few people who are, you know, a few years out of college. Maybe like 5 to 10 out of the 30.
Okay, cool. So I guess this is probably like a funny question. Why did you choose Striveworks after grad school going in? I'm sure you must have done like a general job search or whatever, just for advice for people graduating looking for industry positions, I guess.
Yeah, I mean, I thought they did, I don't know, I thought the work they talked about seemed pretty interesting. I like the idea of you know, working at somewhere smaller where you're a little bit farther away from that. Sort of one of the things that made me leave academia was sort of this long turnaround time. And I feel like you get a smaller version of that if you work at somewhere big. At the same time, you know, it's a pretty successful company that seems to have a lot of potential for growth, in my opinion.
Okay, thanks.
Hi, something I was wondering was how structured is your kind of day to day? Because like as a graduate student, kind of have a decent amount of freedom in terms of when and how you work. I was wondering if it was kind of that kind of environment at Striveworks, or more kind of you're expected to be kind of on the clock.
No, it's pretty flexible. Yeah, so yeah, there's certainly not like, I mean, unless there's, you know, something important happening, which is not usually, you're pretty flexible in the hours you can work, just as long as you get your work done.
Okay, cool.
And where are you guys located? Where's the office?
Oh, that is on the next slide there. So it's like on Anderson and Mopac. Okay. These are
I guess I'll check the live chat if there's any. Yeah, it doesn't seem like anybody has questions from the stream right now.
Okay.
Any other questions?
Yeah, how often do you guys like go to conferences, publish, or how much of that do you guys get to do or want to do really?
So we've talked about doing that in the future, but as of right now, we don't have any we don't have any like conference submissions or anything like this.
Okay.
All right, any other questions? If not, I'd like to thank Abe for coming here. Abe, if you could pull your email back up on the other slide as well, if anybody wants to contact you. If you guys want to write that down, I guess I can put it in the. That way people can just copy and paste it. But yeah, thanks, Abe. Thank you again. Thank you guys for coming. And if you have questions, also feel free to shoot an email to Abe as well.
Thank you guys so much. This was a lot of fun.
Yep.
Thanks, Matt.
Thanks.